All right, so let's get started. So today we are going to talk about the cameras relationship between two translating camera. Right. So last class we talked about if you have two frames, like one camera capture one image, and then you rotate the camera capture another image that's one in blue, one in red, and we talk about the relationship between these two images can be described by homography. Okay, and then that gives rise to the applications of stitching images into a panorama. Okay, so that's a rotating camera, right? So if you have images that are rotating, that capture different images that captured by a rotating camera, these can be described by homography, and you can stitch them together into a panorama. Okay, so this is just a quick overview of what we talked about last time. The way you can stitch an image is to detect key points from each image independently, and then you match key points. For every key point, you run the two nearest neighbor rule to find the two closest neighbor from the other image. Okay, and then you want to make sure that if the two nearest neighbor, the first nearest neighbor and divided by the second nearest neighbor, if the ratio is small enough, which means that this feature is distinct. You can find a distinct match. Then you declare that, oh, this is a match. Okay. Once you have a collection of match points, correspondence, you can figure out the homography. Okay. And here you need to do the homography using RANSEC because many of the matches may not be correct. Okay, so you don't know which one is correct. So the way you do this is that you sample, every time you sample 4 pairs of matches. Each pair you solve a homography and make sure that you use that homography hypothesis to check how many of the rest of the matches agree with this homography. Okay, and then you go through the say 100 hypotheses and then you rank like votes which one of them is the best, right? And that's how you get the homography. And once you get a homography, you can combine them, right? So you basically walk the image one image to another, and then blend them together. All right. So all these are the multiple steps that built into probably every form right now has this panorama like algorithm. All right. So it's pretty common now, but it's actually pretty exciting like probably 15 years ago. Okay. So it's probably the first time where the computer vision algorithm built into like a commercial hardware, like the cell phone here. All right, so this is about images that capture from a rotating camera. Let's see. Image captured by a rotating camera. And this class, we want to move forward to talk about what happened when you have two images captured by a translating camera. Okay, so there we need to talk about two things. We need to talk about so earlier we said that rotating cameras, the two images are related by homography. And what's the mathematical relationship between matches from two images captured from a translating cameras? So it has a name called epipolar in geometry. We will talk about that. That's kind of, if you have a matches points, how do I describe the relationship between these two matches? And then based on that, we'll talk about how you can recover the depths from a stereo matching, right? So if you can have two images, and then how do you figure out the depths? Okay. So this is the main core application we are going to talk about. Basically, you have two cameras. Say you have a camera capture this, and then shift the camera positions and capture another images, right? So your goal is to say you have some particular point in the 3D space, but you want to figure out how far that point is relative to the camera. Okay. So this is the stereo vision problem. So we have that built in. We have two eyes, and then then you can figure out how far an object is, right? So obviously this has a lot of application, right? So if you think about self-driving cars, think about any robotic system, that you need to knowing what object is, how far away an object is super important, right? So if you don't know that, you could easily bump into a person, like kill someone, right? So or kind of crash, right? So make that this is important because it helps you figure out the like what are the space that you can move. Okay. All right. So so we'll talk about this later on. And it has this kind of the motivating applications. So we have two set of problems, right? The first one is it's called calibration, right? So basically, we need to know, like, if I have two cameras, how do I know the relationship between the two cameras, right? So is it like translation or is there some rotations here and so on? And then we need to find, once we know the relationship, we need to know how to match from one point to another point in another image. Okay. So this is a correspondence problem, right? So we already talked about this but sometime we talk about a couple of correspondence problems, right? So let's see here. If I have two images, like basically take one image and then you move around and then take another image. Okay, so if you have two images, now I said the bottom left corner of that window is something that I want to determine what's the depth of that point. Okay, so the question is, how do you find a correspondence search in the right image? Okay, so we already talked about several different methods to find the correspondence. Okay, can anyone give me some example? If I have a patch, a point on the left-hand side, what are the possible methods that we can do this match? Yes? Six. Yeah, we can do, let's say, we just say that point is the local interest point, and we extract some features around that regions. And at the same time, we extract a couple of features on the right-hand side, on the right image, and then we try to find them. We try to do the feature matching. Okay, that's one. Any others? Yes. Sliding window. What do you mean by that? Template matching. Okay, yeah, that's also a method. Basically, you let's say you maybe define a 5 by 5 or maybe 15 by 15 window around that red cross, and then you take that as a template, and then you go through the second image, and then kind of scan through and pick a one that's the highest response. Okay, that's also one. Any others? Kind of correspondence problem. How do you solve the correspondence problem? So we talk about two seed features and temporary matching. I think there's a third one. How could you solve this? Any idea? Lucas, yeah. So when your images are maybe they are not too far, they don't change too much, then you can solve this with Lucas candidate tracking algorithm, right? So you start with that local regions, and then you try to find that. Okay. So all these are valid approaches. Okay. There's some kind of there's something that we didn't consider, right? Because either you use C features, you need to find for each feature, you need to find every other features in the second image, right? And then for the optical flow, you also need to search locally, right? You assume that that feature doesn't change too far, right? So it's kind of very it doesn't change too far. And temporary matching, you need to search for all possible locations. right? So, but if I tell you that these two images are captured by two cameras of the same static object, right? So this is a building, this is a move. And in that case, the key idea is that can we constrain our search, right? In template matching, I need to search in two-dimensional. But the key idea here is that because if I know these are static objects, so they don't move in 3D space. So these two images, they have some underlying relationship that allow us to limit the search space from 2 dimension to 1 dimension. Okay, so that immediately make it things much, much faster and make much more reliable. So this constraint is called epipolar constraint. Okay, so where does that come from? Okay, so here is a kind of some terminology here. We'll go through the math later on, but basically what you see here is that you have two cameras. Okay, you have two cameras, and the left-hand camera O is the camera center of the left camera, and O plot is the camera center of the right camera. Okay. So the key idea is applying, okay? So I have a 3D point in the 3D space, that's X, big X. And that point gets seen by the first camera, O, the camera center, by seeing, I mean, that's basically literally draw a line from that point to the camera, right? And that get intersect at this small point, X, okay? So basically, this point in 3D space X is being projected onto the first camera, O plumb, okay? And at the same time, it gets to project it onto the other X plumb. The other camera get projected onto the X plumb. Okay, so now if I have particular features, I want to find a match in the second image, right? So I have this point, X. I want to find where that match, that correspondence is in the second image. Where do I search? Previously, if you use template matching or Lucas-Canedy algorithm or C features, you basically search everywhere in the entire image, right? You don't have any constraint. But there are some geometrical constraints here we can leverage, right? The constraint comes from the following. So imagine that you have a 2D point here, that this is what you see for the 2D pixel. This is a point for a particular 2D point, okay? And from that viewpoint, you don't know what the depth is. You don't know where that point goes. You only know that from this viewpoint, you see a pixel that's an object project onto X, right? You don't know where the depth is. What you do know is that that object must align on a line from this object center to this point, right? It must lie on this line, right? It must lie on this line, and no matter what the object is on this line, each point will project onto the second camera along a line, okay? Which means that if I want to find a correspondence between X and X plumb, I know the corresponding point X plumb must lie on a line. Does it make sense? They will not lie on every other locations. Okay? So this point must be, you can find the correspondence on possible location here, depending on the depth of this point, right? So when you do the search, you don't need to search for all the possible location. You only need to search over a one-dimensional positions. Okay, does it make sense? So this says that potential match for X have to lie on a corresponding line in L plumb. Okay, it must be lie on this line. Okay, So same thing happens in the other direction. So this point, if I have, so the reason is what I said is you don't know you don't know where that point lies on this ray. Okay, so you could be this, you could be this, you could be this. Okay, you could be near these locations, and therefore it must be lying on a line. Okay, same thing happen from the other side as well, right? So if I have a match here from the X palm at this point, I don't know where they are. It must be this point, but I don't know where the point actually is on this ray. But all this ray will be matched, will be projected onto a line in the left image. Okay, so a potential match for X palm will have to lie on a line in L on the first image. Okay, so this is simple geometry. You have a two camera capturing and translating. They have some unknown translation and rotation, and if you look at the 3D points, it must be the case. So it looks like this, right? So you imagine that you have a in 3D. So you have two cameras, that's O and O prime, and the object center, the camera center O and O prime, and the 3D object, you can think about they have a 3D plane, right? And they lie on 3D, and that 3D plane and the image plane must intersect. Okay, so this is from simple geometry that give you this relationship. Okay, and this is the concept of epipolar constraint, right? So because of this perspective geometry, that'll give me that the idea that if I want to find a match from a particular point from left image, the correspondence must be like on a line. Okay, the same thing happens from the right image. A point on the right image, you can find the corresponding point on a line on the left image. It's not everywhere. It's not in the 2D positions. It must be on line. You can find that correspondence there. All right, so just want to make sure that this concept is clear. Does this make sense? All right. Okay, so some terminologies before we move on. So the line that connect the two camera center is called a baseline, right? This line is called a baseline that's connecting to the camera centers, and the intersection between these lines and the cameras is called epipole. Okay, so this line, the intersections, epipole is the intersection of baseline. This line, they must be penetrating to intersect with the image plane, and that image plane is called epipole. Okay, so you can also think about this as a projection of object camera center from the right image, from the right camera, get projected onto the second image, right? Basically see where the object center is, camera center is, from the other image, from the other viewpoint of the left image. Okay, from the left camera, it get projected. This point get projected onto this point. This point get projected onto this point. Okay, and that point is called epipole. Okay, and you can say, okay, so if I have a 3D point X, and I have this plan, this 3D plan, the kind of this triangle, it's called epipolar plan. Okay. All right. So every point on this is called epipolar plan, and because you have this plan, and the intersection between two planes is a line, right? You have this is a 3D plan, and this is the 3D plan. And the intersection between these two planes are a line. Okay, and that line is called epipolar lines. Okay, it's just some terminology, but you get an intuition from these figures alone. Okay. All right. So this is just intuition of how things are related to each other. If I have two cameras, if I have a 3D point, and they must satisfy this. Right? This is from simple geometry that you have this. Let's see how some examples of what that looks like in typical images. Okay. So imagine that you have two images that here I have a vase. I have two images. One, let's imagine that, okay, this is the vase. Then I capture an image here, and I capture an image here. So it's a converging viewpoints, like one viewpoint here and one viewpoint here. Okay. So it looks like this. Okay. So what it shows here is that you can see that if I have a corresponding point, it must lie on a line, right? I don't know which point this point is, but it must be lie on a line here, right? And same here, I have a point, it must be lie on a line. And those lines are epipolar lines. So here, epipolar lines is a bunch of lines that's being it's called a 1D family that's coming from you can think about, so here needs some kind of imaginations of the 3D geometry. So you have the baseline between one camera center and the other camera center. It's a line, right? So imagine that you have some revolving kind of plane that pass to these two centers. And you can imagine that there's some rotations here, like you have some rotation here for all the possible planes that pass to these lines, right? So every plane that pass through this line, it's called epipolar plane, okay? So every plane that you can think about, you have this plane, you have this plane, you have this plane, they all pass through the same kind of line, right? The camera geometry. And the possible epipolar lines are intersection of that epipolar plane intersect with the image plane. Okay? Can you imagine this? Like you can imagine that these, if you have different x, you can span through all the possible epipolar plane, and you get multiple different lines like this. Okay, and that gives you like something like this, right? So from epipolar plane, this is the baseline, and you have two image planes here, and everything that's connected to the epipolar plane that's coming from all the planes that pass through this baseline, and they intersect by these guys, right? So that's why you have these epipolar lines. Okay, makes sense? All right. So this is images captured from two cameras from like convergent views. But what if you have images that are horizontal, right? So I don't do this convergent view. I take a picture here and I translate only, capture this. In this case, you have something like this, right? I have essentially the baseline and the image plane, they don't intersect, right? So the epipole, so your epipolar plane is essentially sweeping like this, right? So this is the baseline. All the planes that pass through this baseline is all the planes like sweeping through the space. And the intersection between those planes, and in this on intersection of these epipolar planes with the image plane will be horizontal lines. Okay, so there will be get something like this, right? You get something horizontal lines. Okay, so these are two examples of different viewpoints. So another interesting thought experiment is that what if I have an image, capture an image like this, first image, and the second image, I just move forward and capture another image. What will happen? So imagine that you have a self-driving car, right? So you have an image, and then you capture another image forward. What would the epipolar line looks like? Basically, the idea is that if I want to find a feature matching for one image at first image, where should I look for in the second image? If I have a camera that capture the image here, and I move forward, capture another image. Yes. New line will be about the previous one. What would that look like? This is like a in the previous case, the epipolar line looks like a converging lines. Here, like if you have capture like this, and if you are horizontally only, you get something that is parallel. So the question is, if I have two images that are forward motion, one image here, one image here, what would the epipolar line look like? Any idea? Yes.
Would it still be like converging, except the plane would be like tilted?
Converging. So can you describe like an image here, and what would the epipolar lines behave?
Not a. Would they not diverge?
Diverge. They probably will diverge, right? So basically, you need to think about where that you have to think about in terms of epipole, right? So think about all the epipolar lines, like basically the lines in projected onto the image, will pass through the epipole. Okay, so epipole is the projection of the other camera center onto this camera. Okay, so if I have moving forward, what's the projection of the second camera onto this? It will be probably at the center, right? So what the epipolar line pattern looks like if the epipole is at the center. Remember, all the epipolar lines will pass through the epipole. Any idea? Yes. Straight up, but that's only one line only, right? Epipolar lines are a family of lines. So if you have a point that epipole get projected, the camera center of the second camera projected onto the first camera, that location is the epipole. Okay, so imagine that this, right? This example is I have two cameras, one camera here, camera 1, camera 2, okay? And the epipole E is the projection of this point onto the other camera, okay? And all the epipolar lines will pass through this point, okay? So that's why you see that in this case, the epipole is probably far here, right? Because all these lines, they converge onto there. Okay, so now if I have two images that's kind of forward, and which means that the epipole is a center point of this image. But what would the epipolar lines look like? Yes.
Would be like the lines like extending from the center,
Mm-hmm.
and then for the second image, the same thing. Closer.
Yeah. So okay. So the answer is correct. So because every pole is at near the center of the image, and because you know the epipolar lines must pass through that point, and therefore it's kind of like star shape, right? So which means that it will look like this. Okay. So these are two images. One, like say, so you can imagine that this image is a forward image, right? Than this one, right? So they are related by these things, which kind of makes sense, right? It means the following, right? If I want to find if I take an image here and I take another image forward, the way I can find the correspondence is this radial ray, right? Because you can see that if you move forward, everything can kind of expand, right? the way you can find the correspondence, it must lie on these lines, right? You don't need to search everywhere. So the key idea is that if you know, you can, that's why you need to figure out what the epipolar constraint is, and therefore later on you can find the stereo matching much more efficiently because you only need to find this kind of algorithm. Yes.
You can't get like that from this, right?
You cannot get that from this yet. Yeah. So you need to first figure out what the configuration of the images is, and then when you find the correspondence, you get a configuration so that you know what the constraint is, right? In this case, when you find a point, you basically need to find you can search over only this line, right? So you constrain your search space, and once you figure out the correspondence, actual correspondence, you can figure out the depth. Okay, so that's kind of the core idea of all this. All right, so far we have zero equation, but now you understand the epipolar geometry. Basically, very simple geometry. We have two images. You don't know the rotation, translations, but they must satisfy these kind of epipolar line constraints, right? If I have a point match, it must be able to find another point on the second image. It must be line on the line on the second image. So, but how do I mathematically describe this? Where does that come from, right? So from simple geometry, you can describe this, right? Intuitively, you can know this. But now we need to go a little bit deeper. Like these are the things that kind of random people can understand, but you are not random people. You are computer science major, so you need to kind of dig a little bit deeper. All right, so let's go through the math. Okay, so here's the again a 3D point, and I have a first camera, and the first camera has a coordinate system x, y, z. Right here I have x, y, z, and I have a camera coordinate system. So you can imagine that the projection of this guy is just drawing a line to here, right? So drawing line. Think about this: the pinhole camera. This is the camera center, and the projection is just drawing a line, a ray project onto this point, and you get a project onto this 2D locations in orange. And this, let's call this a left camera. Okay, this is left camera here. And at the same time, I have another camera, like say this is the object, this is the X, this is the point. I capture this point image, and I have a left camera. The left camera, it has its own coordinate system, right? So this camera has a coordinate system here. This right camera has another coordinate system, okay? So like look like this. So I label the coordinate system, the superscript L and superscript R. Like this guy is the right camera, right? At the same time, this camera will go get projected. This same 3D point will project it onto the second camera. Look like this, right? So you have a right camera, right? So far, still no math. But you can say, okay, so we have this so-called baseline that's connecting these two lines, okay? To center, that's called baseline. All right, so far, so good. Okay, so let's now try to understand how do I mathematically describe the epipolar constraint that we just know? Like we know that this point has a line, the correspondence line, but how do what's the mathematical relationship between them? Okay, and then why that's the case? All right, so because the reason is that once we figure out the mathematical relationship, we can figure out what that how do I estimate that from feature matching? Okay, so let's see. Let's first do the following. I can explain these 3D points, XL, YL, ZL. That is a 3D point position from the eye of the first left camera. Okay, I have a 3D point, and I can know the 3D point positions, but describe that 3D point position from the left coordinate system. All right, so this guy. Okay, at the same time, I can also describe the same 3D point, but from a different coordinate system, right? These two things are the same, but the numbers are different. The numbers are different because they are described from a different coordinate system. Okay? So far, so good? Yes.
How are we getting the depth?
We don't know the depth yet. Yeah. Okay. So there must be some coordinate system, right? We don't know the depth yet. Okay. All right. So we just know that it must be some coordinate system here, some coordinate system here. We just want to derive some constraints. Okay. So and there's a relationship between these two coordinate systems, right? That two coordinate system is by a translation and rotation. There must be some translation applied to the left camera to here and a rotation, right? There must be a rotation and translation relationship between these two cameras, right? So it's described by rotation and translation. All right. So, and then we talk about there's a plan here that connect the two camera center and the 3D points in the space. So it's like 3 points define a plan. Okay. All right. So now we need to derive what does it mean to be there's a plan here, right? So how do I the thing is that how do I derive that epipolar constraint? Okay. So the key equation here is that look at this geometry, what it says is the following. What it says is the following. Is that these two, like I have this XL, this is this ray, this vector, this called XL, and I also have this T. Like this vector is called translation. It's a translation. This T. Okay. So I know that these two vectors lie on expand a plane, right? So the way I can describe this is the following. Is this guy, okay? So what is this guy saying? Is that if I take the T vector, this translation vector, take a cross product between this T and the XL, you get cross product, you get some vector that's perpendicular to this 3D plane, right? So again, you have 3D plane, you take the T and the XL, T cross product, this vector and this vector, do the cross product, you get this vector, right? And that vector, this vector is perpendicular to any vector on the plane. And I happen to choose that vector as XL. So the way I said two vectors are perpendicular to each other is that their two dot product is 0. Okay, so now I have my first equation like this. That so far so good? Make sense? Right? Okay, so now I want to basically derive okay, so the key is that I want to derive a relationship between these 2-point matches, right? How do I describe this 2-point matches? Right, so this is XL and T across XL, but it still doesn't tell us anything, right? I want to, so this is the normal, there's a T cross XL, this vector cross product with this vector, and this is going to be normal, and you get this, okay? So now I can describe this, right? So now I can say the dot product between XL, it looks like this. It's XL, XL, YL, and ZL. That's this component here. It's a vector. The vector product between the 1/3 and 3/1 and equals 0. And this guy T is a translation TX, TY, TZ. And the cross product can be described like this. Okay. All right. So this is just high school math. But something that's a little bit more interesting is that this TXTL, it's kind of hard to work with because there's kind of TX, LYL, T minus TY, XL. But I can make it easier to work with. Instead of using the cross product, any cross product between two vectors can be described by a matrix vector multiplication. Okay, so you can see that I have these are just the linear combinations of XL, YL, ZL. I can write the same thing into matrix multiplication like this. So this guy is a matrix vector product. It's the same thing as the cross product between T and XL. Okay, so I'm not doing anything. I just said that these are the things. All right, so this I can write this as a matrix vector form. This is just a translation and XL. So far I have this guy. Okay, so I can write this more compactly with this guy. Okay, so this XL is just XL, YL, ZL, just 3 elements, and then transpose become row vector multiplied by this X big matrix, 3 by 3 matrix X, and times this guy must be 0. Right? They are 0 because it's basically this relationship describes that translation vector and the ZL lies on a plane. That's just the relationship here. Okay? All right, but here it only has the relationship between the XL and XL. But I don't want that. I want to relate the two cameras. So here is the trick. I want to be able to describe this XL, YL, ZL as from the other coordinate system. All right. So remember that we talk about that these are the same point, right? So this is the same point being expressed from the first left camera's coordinate system, and the XL is the same point described by the right camera coordinate system, and they are related by a rotation and translation. What it means is the following: that I can describe this XL, YL, 0 as a rotation and translation of the XR, YR, ZR. Does this make sense? At the same point, this is being described by two coordinate systems, and the two coordinate systems are related by a rotation and translation. That's it. Okay? So here's the interesting part. I have this simple relationship, right? Basically says that the expression of the same point is expressed from the left camera can be described as a rotation and translation of the coordinate expressed on the right camera, because they are related by a rotation translation. Okay. So far, so good. All right. So this is a little bit messy, but but you get the idea. Okay. So now I have these two terms, right? So what I would want to do is just plug in that right-hand side to the part of the left-hand side. Like I want to replace that XL with this guy, okay? Because if I do that, I have an expression that related to XL and XR, right? I know the two relationship is. Okay? So it looks like this. I just plug, and what I did is just plugging this guy XL with this guy. Okay, I get something like this. All right. Okay, so then I will expand this because it's a plus, and it will have two terms here. I have two terms here, and these terms. Can anyone tell me what this term is? I have Tx is basically this normal. Okay. What's the dot product between this Tx and T? Okay, I have a cross product, and a cross product dot product with itself. What that value is? It's 0, right? So this guy just goes away. Does it make sense? This Tx, this cross is then normal. Basically, it's normal, and the normal is perpendicular to any vectors on the plane. And t is one of the vectors on the plane, right? So this dot product must be 0. So you just go away. So you will have something, sorry. You have something like this, okay? Make sense? All right. So and then we can say the tx this cross product and this guy. I don't know what that is, but I can just say it's a 3x3 matrix. And that 3x3 matrix, we give it a name called essential matrix, right? That's essential because they relate. This is how you relate it to cameras, okay? Related to cameras, okay? So you have these expressions like this, okay? So what it says is that 3D point position, if I have the same 3D point, the 3D point position expressed in the left camera coordinate system is this guy. And then you have essential matrix, and the 3D position in the right camera coordinate system, it must be equal to 0. Okay? All right. So, but still, it's not enough, right? So this is just says that that the 3D point, but all we have access to is 2D projections, right? We don't have the depth. Remember, we don't have the depth. So what we could do is that we know these points are related by I only know UL, VL, like the 2D position of the point, and UR, VR, that's the 2D positions of the point, right? So you know that this 2D position is a projection of XL, YL, ZL projecting onto the left camera. It's like this. This is left camera intrinsic, right? So this projection is basically just a scaled and shifted versions of that. Okay, so you have a Z, UL, VL, and this guy. Okay, on the right hand side, you're also projecting this point onto this guy. Okay, which means that you can express the left hand side, this guy, as expression of UL, VL, and 1. Okay, and the same thing, XR, you can express the same thing as this. Basically, you can express like this. Just take the inverse of the intrinsic. Okay, you have this something like this. Okay, UL, VL, 1 and times ZL and this guy and this guy. All right, so you don't know, again, you don't know the Z, but you have this expression. On the left hand side is the 3D position from the left camera, and on the right hand side is the same 3D positions on the right camera. Okay, you can express this in terms of their projection and to take the inverse and multiply by the Z. Okay, so remember this. I have this. Basically, take this ULVO1 and then take the inverse of that. You can express this guy as some function of this guy. Same thing here on the right hand side. Okay, you have this. So what you need to do is to plug that in to the equation like this. You can replace this guy, replace this guy with this guy, replace this guy with this guy. All right. So if you plug this in, you'll get something like this. All right. So again, it's kind of a little bit complicated, but you have something. It's still a 3x3 matrix. 3x3 times 3x3 times 3x3. It's still 3x3 matrix. And you have some Z that you don't know what that is. It's a constant, but it's some value, and it's also some value. And multiplying everything together, it's 0. Okay? You have an equation that says it's 0. But because this is kind of some scalar you don't know, you can just say and the whole thing is 0, which means that the rest must be 0. It doesn't matter what this value is, right? This value is, so you can get rid of it, right? So just imagine that you have some equation times the scalar equals 0, it means that because that scalar is not 0, which means that the rest of the equation must be 0. Okay, so you can get rid of this. So it's fine. You don't know the depth. Okay, so it doesn't matter what the depth is. Right, so you can get rid of that. Then you have the following expression. Okay, so what it does is that your 3D point, your 2D point in one camera, in the left camera, is related by the corresponding point in the right camera, and some fundamental metrics that describe the relationship between two cameras, right? That's coming from the rotation and translation, and the whole thing multiplied together is 0. All right, but what does that mean, right? So I have this, and this is called fundamental metrics, by the way. Okay, what does that mean? Why do I kind of go all the trouble to derive this? Okay, so it looks like the following. So what you can do is the following. Okay, so you have this fundamental matrix. Okay, so here is it's basically the reason why this is good is that it tells you precisely when I give you a point in the left camera, this is the point in the left camera. This is the pixel coordinate of the point in the left camera. If I know the f, so I have f times this guy, the right coordinate system. It means that the other way. So if I know the point here, if I know the point in the left camera, and I have a 3x3 matrix here, so 1/3 times 3/3 is 1/3. Okay. So look at let's call it this vector times this matrix. Let's call it ABC. Right. These are three numbers. Right. So what's left is ABC dot product with UR VR1. So what does that equation look like in terms of UR VR? I have A times UR plus B times VR plus C. What does that equation look like? Any idea? I have A plus UR plus B times VR plus C. If I plot that, what does that look like? Yes. It's a line equation. Okay. So which means that if I know the f, then given any point in the left camera, I get a line equation in the right camera. Does it make sense? Which means that if I know a point in the left camera, if we multiply this, post-multiply by this f, I know exactly where I should look for the correspondence. I know the correspondence. I don't know the depth, but I know the correspondence must lie on a line. So this is the mathematical description of the intuition we just talked about, right? We know from visually it looks like there's a line, but I don't know how to find a line. But I'm telling you that because the derivations that you have these three things multiplied together, they must be 0. And that thing actually tell us if I have a point, this multiplied by this, it becomes a line equation for the other one. Okay? And the same thing happens the other way, right? If I have a point in the right camera, it's a point in the right camera, you have a 3x3 matrix times the 3x1 vector, you get a 3x1 vector. Let's call it ABC, and then you have A times UL, B plus B times VL plus C, and it's become a line equation from the left camera. All right, so this is basically just formalize the concept of epipolar constraint. Right, so we have this f, then we can, like, if given any point, I can find the correspondence. Okay? Yes.
Where's this line?
So on the image, yeah. So it depends on whether if I have a point in the left camera, then the line is on the other image. Okay, so they tell you where to search. Okay, so because of this, but now the question is that how do I find this f? All right, so because we know that f, if I know the correspondence, and I can solve for f, right? Okay, so if I know the f, then given any point, I know where to find the correspondence in another image. Okay, so if I know the f, I can use the solve correspondence. But now, if I have C features from the feature matchings, and then I can figure out if I know C features, I can do the matchings, and then I have something on the left-hand side and right-hand side, right? I have correspondence. These are points that are correspondence. And from the correspondence, we can solve for f, okay? We can find that what the 3x3 matrix is. And usually what you could do is that you could figure it out because you have 3x3 matrix. Then if you also know the intrinsic, that is the left matrix intrinsic and right matrix intrinsic, you can figure out the essential matrix. And once you figure out essential matrix, you can decompose this into translation and rotation. Okay? Does everything make sense? All right, so just kind of recap what we talked about so far. From this figure, it's any x that's u naught v naught. Sorry, u l v l. This vector is a point here times f x plum equals 0, right? So which means that f times x plum, this x times f plum, is basically says that if I have a point in the right camera and f plus plus wrong is let's call it L, and this L is a line, describe a line in the left camera, right? And the same thing happens here. If I have a x, if you take the f transpose x is an epipolar line, is a line equation in the right camera, okay? And if you apply the epipole, it will be 0 every time, because the reason why this happened is because it passed through the epipolar line. Sorry, the epipolar line must lies on this epipole. Okay? And what if I have a matrix, a 3x3 matrix, and I have a vector that's not all zeros? If I have f times a vector equals 0, what can I say about this matrix? If I have a matrix here times a vector, but that vector is not all 0, but I get 0 out of it. What can I say about this matrix F? Like, so this probably need to refresh your memory about linear algebra. If I have a 3x3 matrix, I have a vector multiplied by that matrix multiplied by that vector, it gets 0 out of it. What property can I say about that matrix? Any idea? Yes. What can I say that again? It's not invertible. Yes, it's not invertible. Can I say something about the rank? It's not going to be a full rank matrix, right? It's going to be only at most rank 2. Okay? And what is that vector called? If I have a matrix multiplied by this vector equals 0. What is that vector called, by the way? The idea? It's a null vector, right? No subspaces. Okay, so again, this is some linear algebra things that we use. And another way, the multiple different ways to describe the same thing, right? So it's not invertible. It's a full rank. It's only rank 2. And the way you can describe this is that if you compute a determinant, it's going to be 0. Okay. All right. So and what are the degrees of freedom of this, right? So F actually have you can compute, because F comes from this guy, right? Come from this guy, and this guy is from rotation, translations, and then K and these things. It has only 7 degrees of freedom. So basically, you have 7 things that can move together. But you have 9 entries, but up to scale, because the whole thing is 0. But you can multiply the whole thing by some scalar. It's but you can scale. Okay, but it only has 7 degrees of freedom. But usually we want to the popular method is called 8 points algorithm. So let's see what that looks like. Okay. So again, we probably only have one single algorithm used for most of the computer vision problems, right? The way we try to find is the F is that we know the relationship, right? We know that if I have a pair of correspondence, they must satisfy this equation. Okay, this pair of correspondence must satisfy these equations. So what I did is that I just take X is U V and X pawn is U naught U pawn V pawn. I just expand this, right? You just multiply this everything together. I get expand this. I get an equation. So here, every pair of correspondence UV match to U pawn V pawn, that you get a correspondence from matching C features, right? U pawn V pawn, and then what you do is like every other algorithm we apply, is that you want to figure it out, because you know that if I have a correspondence, it must satisfy the F, that equation. But here, you don't know what F is. You don't know what F is. So you want to estimate out what the F is. So what you do is that you just expand this, expand the equation, and then pull the unknown into a column vectors. Okay, put an unknown into a column vector, and the known part as a row vector. So you get something like this. Okay, so here you have 9 unknowns. Okay, 9 unknowns, right? So this is a 3x3 matrix. So you have F11, F12, F13, all the way to F33. So you have 9 unknowns. But because you know that they are up to scale, right? Basically, it means that if I have a solution, if you scale it, it's still a solution. Okay. If F is a solution, the 2F is also a solution, because everything multiplied is 0, which means that you have you don't need a 9 equation. You only need 8 equations to solve this. Okay. So if I need 8 equations, and every pair of matches give me every pair of matches, you can see that every pair of matches give me 1 equation only. Okay. So which means that I need a correspondence to figure out this. Okay. So this is different from the homography. In homography, we have every pair of correspondence, because they are related by the homography. They are with X pawn equals to H times X, right? So every pair of correspondence give me 2 equations. And in that case, I only need 4 pairs to figure out, to give me an estimate of an H. But here, I need 8 pairs. Okay? So from this, you set up the linear system equations of A times F equals 0. So we talk about this form a lot, right? So you have a AX equals 0. The way you can solve X is to compute the SVD and then take the the eigenvector corresponding to the smallest eigenvalue. Okay, and then you can reshape it back. It looks like this. You get something like this. In MATLAB, it looks like this. You can take the f like this. Okay. And then after that, you can, because you also know that f, this matrix f, because the correspondence is kind of noisy. So you could have noisy estimate. So later on, what you want to do is to make sure that the rank is 0. The rank is almost 2. And the way you do this, and once you figure out the rank, recover the rank, you get, if you don't do this, it will get something like this, right? So epipolar line doesn't pass to the center. If you if you enforce the constraint, you get something like this, okay? You get corrected. So the way you can enforce the rank is 0 is also through SVD, right? So what it did is that you estimate the SVD, you compute the SVD, and you just, because the least singular values is the one corresponding to the least amount of energy, right? So you just set them to 0. It will enforce that the matrix have rank 2, but at the same time you have a very close to the original f. Okay, so this is how you can resolve the determining this constraint. Okay, so this process is just one method, right? One pass. I give you a point pair correspondence. You can figure it out by setting out the linear system equation. Then you can solve for the f and then enforce the constraint to get the actual f. Okay. What we talked about earlier. Sorry. Go.
Sorry. After this case, just 1 point, right? All
F is for all the points. Yeah. F basically describes the relationship between two cameras. Okay. Okay. Because that relationship holds for all the points. It's from the two cameras. So all the point pairs will share the same relationship, which means that you can, if you have at least 8 correspondence, you can figure out that relationship is. Okay. But there's a problem, like we talk about in the same problem in image stitching, right? Because you don't know what is the right inlier correspondence. Some of the correspondence are outliers. And therefore, what you need to do is that you need to run ransack on top of this simple method. Okay? Okay, so you need to, every time you do sample 8 pairs, so the process is like this. If you have 100 matching correspondence, every time you sample 8 of them, solve for the, so basically it's like this. Every time you solve for ransack, every time you test 8 pairs, 8 correspondence, with that 8 correspondence, you solve for the f, okay, with this algorithm. And then once you plot the f, you need to test how many of these, the rest of the 100 matching pairs agree with my f. Okay, and the way you can test that thing is to take the x, every pair you have a correspondence. You want to test whether the f can explain my correspondence. Okay, the way you test this is to take the point in left camera, post multiply by this f, you get a line. You want to check if this point correspondence is close to the line or not. Okay, so some people will implement this with just this guy, but it's not accurate. Here, this is not accurate. You need to normalize by the line the norm of this the line equation. Okay, you need to really calculate the point to the line. Okay, so you have this equation that is you need to normalize this by the line equation. Okay. All right. So once we have that, you test, like, basically you can accept a point is an inlier to the epipolar for the fundamental metrics if they are close enough, right? If they are close to the epipolar line, which means that it can you can predict that that fundamental matrix can explain your correspondence. And every time if you have 100 correspondence pairs, then every time you sample A pairs, you solve for F and check how many of the rest of the 100 correspondence pairs you can explain. Okay, and that's the inliers. Then you go through, say, 500 trials and then pick among 500. Every one of them, you have some number of inliers. And you just pick the one that has the highest inliers. Right? That's how you can robustly estimate this. Okay, so you can see the comparison between homography estimation and 8-point algorithm for fundamental metrics. Right? So on the left-hand side, the relationship is this guy, and right-hand side, the relationship is this guy. Okay, so the algorithm works very similar. You first normalize the coordinate system, image coordinate, because you want to make the numerical more stable, and then you have a ransack. Either in the homography estimation, you have a 4-point algorithm. In the fundamental metrics, you have an 8-point algorithm. And then you basically estimate the solutions with SVD and then enforce the rank with SVD. And then later on, you denormalize it. And that's basically the basic algorithm for either recovering the relationship between rotating camera or the translating camera. Okay. All right, so this is just show you how important that you want to normalize these things. So this is a kind of 2-image pair of images. If you estimate this with normalized coordinate system, then you get something pretty accurate. Okay. And if you you can further optimize this, just like a bundle adjustment example we talked about earlier. You can once you get an initial solution, you can treat the actual rotation and translation parameters as the free parameters and directly optimize those parameters with nonlinear least square. Then you get kind of more accurate results. But usually, normalized 8-point algorithm works pretty well. Because it's so fundamental, it's very common in the computer visions. So you actually have a song for that.
Is everyone ready? Yes, everyone ready.
So this is the main textbook. So you will see all the content we talked about so far.
The fundamental matrix used in stereogeometry. A matrix with 9 entries. It's square with size 3 by 3. Has 7 degrees of freedom. It has a rank deficiency. It's only of rank 2. Pull a matrix F and you'll see 2 points that correspond to column vectors called X and X prime. X prime transpose times F times X equals 0 every time. The people are constrained in those epipolar lines. Those multiplying F by X results in vector time. The epipolar line. The other 2 passing through X prime, the 3-component vector. Oh, homogeneous design, the left and right null spaces of F are the epipoles E prime and E. All of the epipolar lines would pass through these. Here's a linear estimation example. Take the set of 8.7, construct the matrix, take the SVD and the element of F in the last column of V.
Practice position. This is the video. This is stereo video, so you can see the epipolar line.
Here we go. You try to estimate with.
All right, so you can kind of this video probably summarize like very concisely what we talked about so far. So next lecture we'll move on to like based on this knowledge, we will move on to stereo to really estimate the depth from two views. Right? Thanks.